Hello friends, in this video we're going to cover the general water storage grading pipeline. Now the reason why I say is the general water storage pipeline is because there will be variations inevitably. This is just the general process, and depending on the kind of project that you're doing, if it's very involved and there are a lot of details, then obviously this workflow is going to vary. And we will probably get to do some projects like that in this course, so I will come back to this document and show you what is actually changing and where the pipeline is different in the project that we're doing than what we're going to talk about here. But I hope that this is going to provide you with a general understanding and a template that you can refer back to in the future when you're doing your own projects. And as we're going through this pipeline now in this video, I'm going to also talk about where things are going to be different when you're working on more complex projects that may have additional features and more detail than what we are covering right here. So the way this document is laid out, it begins from the top left corner, and then we're going to go to the right and go down. And to the side here, I'm going to be adding documents of drawings that we have created for different types of dams, so that maybe you can refer to them and see how we have done something in the past. And this document is going to be linked under the description of this video, so you can always come back to it and if you need to remember anything or zoom in for more detail. All right, so starting from the the top left corner, we have the very first step in any project is going to be the brief. And just before we begin, I want to, again, as I already did in the overview video, I want to reinforce very strongly the idea that grading is not design. It complements design, and design complements grading. They're supposed to work together, but they are very different disciplines. And I've been getting a lot of questions during the course of producing this program by people who are interested in it seemingly, but then when I explain to them what the program is actually about, they lose interest. And I completely understand that. I don't mean to say that I judge anybody for that, but I have a feeling that many people are coming with kind of misunderstanding about what this program really is about and what grading actually is. It seems that many people are out there looking for something that would teach them design, earthworks design, and application, but they miss a very important component, and that is grading. And grading is the bridge between design and application. It's a very important bridge, and if you try to cross without having it, it's going to be very difficult, and it will involve maybe a lot of losses, because it is grading that actually informs design in order for you to be able to apply it with a good degree of certainty and accuracy. If you just take a design and you don't perform any kind of volumetric analysis on it and you try to apply that, chances are, and from my experience, these are above 50%, that you will run into many issues. Now, of course, there are people out there who are extremely skilled, and I even know some of them, that they can just take any hand-drawn sketch of a earthwork design and they can just lay it out masterfully and everything will work out. But those people are very few and far in between, and even hiring them is not easy because they have a lot of work. But this is not the case for most projects, and any civil engineering firm will always perform grading before they apply a design anywhere, and it's just a safer way of doing things. So again, in this video we're discussing a grading pipeline. We're not discussing a design pipeline. These are very different things. We are actually not almost at all in this entire program concerned with design. There is some overlap between grading and design because we need to use the criteria and the concept that the design provides. in order to perform our grading. But beyond that, they're completely different things. So again, beginning now from the top left, we have first of all the brief as the very first stage of any grading pipeline. And again, the brief isn't about designing anything. What we're trying to understand is what is the design that has already been made that we need to work according to. So the main thing about grading and the way it differs from design is that the grading assumes that the design has already been created. And what our job is to bring that design to life, because it's usually just a two-dimensional picture. It really doesn't have any meaning beyond pointing out to a certain location and the extent of certain features. And they're just it's just a two-dimensional extent. What the goal of grading is to embed those two dimensions with another dimension, which is volumetrics. And that's the basis on which we can further then deduct information about that design, such as how much it's going to cost, how difficult is it going to be to build something, is it even possible, is it even allowed relative to regulations, and so on. These are not things that you can easily deduct from a design until you actually perform grading analysis on it. So this is what grading really is about. Of course, there are other benefits to grading, such as you can produce nice looking construction drawings as a byproduct of it. You can perform a lot more analysis, and you can also design while you grade. And we're not going to do that necessarily in this course, but it is something that if you are skilled in both design and grading, you can do both simultaneously. But strictly speaking, they are still, even in the midst of that, they remain two separate things. You cannot do both at the same time. So when I say simultaneously, I mean it very strictly. And the reality is that while you're grading and designing, one will always inform the other, and they're going to be in this perpetual feedback loop. But there will always be one being done before you can actually do the other. So this is what I mean by saying that they're completely different, even in the midst of doing both seemingly at the same time. So under brief, again, we're not concerned with designing anything, but we want to examine what has actually been designed and what are the criterias and regulations and kind of larger realities such as storm data and flood data that we need to work within kind of the general framework. So under brief, we are first of all and primarily going to be concerned with grading and regulatory criteria. And regulatory criteria will vary for every place. It's probably going to be different. And the good thing about it is that it is laid out for you already. You don't have to figure it out. All you have to do is seek it out. And even so, that's usually a responsibility for the client. You can just outright say to a client, well, this is what we need to know. And it is their job then to go and find it out, or to hire another person that will go and find it out. Of course, if you know where to find it, they can also hire you. You can offer your services to seek out that information. But strictly speaking, it's not your responsibility to know what the regulatory criteria of a area is. Then you also have the grading criteria, which is connected to regulatory criteria. They go hand in hand, because the regulators will also usually come up with the grading criteria that need to be followed in order to meet regulations. And those grading criteria will also vary for every part of the world. But in terms of water storages, there are four main grading criteria, or should I say four main categories of grading criteria that we need to look at. And these are, again, related to the way we are going to build most water storages. And If you've watched my video on understanding grading, you would probably know what I mean here. What I talked about in that video is that when we're building water storages, we're building them modularly. So we're going to take a dam and we're going to split it or break it down to its building blocks. So there will be an embankment, a borrow pit, a spillway, and in many cases, auxiliary structures. So we're going to need to find the grading criteria for each of those in order to be able to build them separately. And then we can merge them all together into one coherent structure or system. And so the grading criteria will depend on how many building components you have. I have only laid out here the usual ones, which is an embankment, borrow pit, spillway, and auxiliary structures. Sometimes there may be more. And I personally haven't worked on a project that has more, but I can imagine there may be more if you need to tie in a dam with actual buildings somehow in a larger system, or other kind of cases like that. I personally only worked on very kind of strict projects where we just have to build a dam or a larger dam system where multiple dams are connected, or that they are related to roads and channels and so on. So this is what I've been focusing on here, and that's probably the majority of projects you will ever encounter. So a dam will usually have an embankment, so we need to know the grading criteria for that embankment. And I've laid out some examples here of what those elements of an embankment usually include that you should find the grading criteria for. So we have a crest width at the very top. If, say, the embankment is used for vehicle access, then the crest width will be completely different from if it is used just for pedestrian access. Or if it's used for cattle access, then of course it will be different grading criteria. So we need to find what that criteria is relative to what the use of that dam is going to be in the long term. And this is the important point. We should think about these structures in the long term because they are long-term structures. They will be there for a long time and they're very expensive. So we need to think about them in that way in order to be able to make structures that service people in the long term and make back that investment, ideally. We also have the batters of a dam, which is a downstream batter and upstream batter usually. There may be more batters than these, such as if the embankment has certain extensions to it. Those extensions may have different batters than the main batters of the embankment. So just think about what the project may actually involve and then seek out those grading criteria. Of course, during the course of a project, new things may come up, new necessities, such as creating those leg extensions. You don't necessarily know that you need them right from the beginning, but during the course of a project, you may realize that they're necessary. Then you can go to your client and talk with them about it. And if they agree that those need to be included, then you need to find the grading criteria for those as well. Then we also may have auxiliary features on the embankment, such as any benches or the keyway, if that is necessary. And you will know if these are necessary because the regulatory criteria may require them, or geotechnical investigations may reveal that they are required. So you need to know also the grading criteria for those. Then we have the borrow pit. And again, that is basically the excavation area from which we normally take the material to build the embankment. And that will have its own grading criteria. So at the very least, we're going to have the depth, the slope of the cut. So this is the batter slope. It may be a ratio or a percentage. Usually it's a ratio, so maybe 2-to-1, or it varies. I'm just giving an example, but this is what we mean by that. And the same also for the embankment batters. These usually come as ratios. Then the borrow pit may have benches. So it may not necessarily be just a very simple cut. It may be terraced. And there are many reasons for that. One is for growing plants. So some plants may require different depths of water to grow on. So that may be one reason to have benches in the borrow pit. Then we have the spillway, again, that will have its own cut slope. The bottom of the spillway may have its own slope. So if we zoom in here, we can see we have here a spillway, and the spillway floor itself has a slope on it. This just to facilitate water from moving from the entry of the spillway or the inlet towards the outlet, where then it can flow down the return slope. And so there will be an inlet width and an outlet width. And those will depend on many factors, including storm data. But again, it's not your job to actually design those. And this is where I think many people are kind of worried that they need to figure that stuff out. If you're strictly focusing on grading and you're not presenting your services out there as that of a designer, then it is not necessarily your responsibility to know any of this or kind of be able to figure it out. You just need to know the grading criteria, and they need to be provided to you. So somebody else has to design all of this stuff in accordance with regulations, and then they provide that design to you and those grading criteria, and it's your job then to build all of that in 3D. And there may be auxiliary structures for every dam. So you may have settling pools, which will at the very least have a cut slope and a depth. Sometimes they may have an embankment, depending on the design of the settling pool. And they may also have a spillway. Many people may require that you design a beach, or sorry, not design, but grade a beach. So that will have its own grading criteria, as well as islands, roads, channels, and so on. So the brief stage is really important, and it actually takes the most amount of time. All of this stuff from this point on, so from here, let me draw some, from this stage all the way down, all of this stuff may take something like 15 minutes to actually go through all of this. And this stage may take many days, even longer than that, depending on who you're actually working with and how fast they can look for that data and provide you with that. So there's just a lot of information that you need to get from the very beginning, because unfortunately grading is this kind of a discipline where you cannot proceed forward without this information. You need to know all of that stuff. And apart from the grading and regulatory criteria, you also need to know the storm information, at the very least for the last 100 years. And I would nowadays even say go as far back as you can, possibly 500 years if you can find data like that, because honestly, I don't want to get into the whole climate change thing, but we have been building structures according to the 100-year data, and they just weren't sufficiently sized, and they had issues and had to be resized during a storm because they just weren't large enough to accommodate those 100-year events, because they're just bigger than the 100-year events that were recorded in the past. So nowadays a practice is to slightly oversize things, because usually we cannot easily find more than the 100-year flood data. So unfortunately we kind of are in the blind, so we have to oversize structures like spillways, and to be able to have some buffer against events larger than what has been recorded. And you're also going to need survey data. Again, this is something that you cannot proceed without. And that survey data has to be of sufficient quality for dams, as well as any other grading. But for dams, it is important that it's of very decent quality. And this is because dams are very expensive structures, and you need accurate data to work with, especially in the vertical aspect. And you cannot just afford to work with low resolution data, unfortunately, because when it comes to volumetrics, the way volumetrics are calculated is based on the accuracy of the vertical data. especially, but also the horizontal data. They work together. And if that data is incorrect, it's going to be reflected in the volumetric analysis, which in turn is going to be reflected in any costings that you derive from that analysis. So you really need good data, and I cannot tell you what exact accuracy that data should be, because it's going to vary depending on the project. But I would personally never work with data when it comes to grading that is less than 1 meter per pixel resolution, and which already excludes much of the world, unfortunately, and in terms of widely available data. So that would mean that a surveyor has to be hired usually to prepare that data, and that's very expensive. And that's not, 1 meter per pixel resolution data is not very good even for this kind of work. Ideally, you would have something down to 0.1 to 0.25 meters per pixel resolution, and that's expensive. Anyway, you are able to find it, even if it's available from governments, or you may have to buy that, and it's not cheap. Even more if you have to prepare that data yourself or hire somebody to do it. But we cannot afford to work with low quality data because it has so many consequences down the road that is just too risky, unfortunately. So I would suggest that if you're going to work with survey data, that you find the absolute best that you can. Try not to compromise on it too much, because it's absolutely fundamental to everything we do in grading. And after we received all of that data, we need to optimize it. As I talked about in the video on understanding grading, optimization is one of the key things that we need to do. It's not something that is difficult. It actually takes just a few minutes, but it can save you so much frustration and hours of cursing at the screen. Because usually because grading requires such high quality data and high resolution data, that data will normally come with a lot of noise in it because it's such high resolution, and we need to clean it up in order to be able to actually use it in grading. Because if you just plug it into the software the way it is and try to perform grading functions or grading processes on it just the way it is as raw data, I think in most cases the software will crash, or at the very least you're going to experience so much artifacting in your models that they will be basically useless. So if we just spend a few minutes preparing the survey data, we can avoid all of this. And I have covered in this program how we do that. Mostly it's just focusing on the topographic data, but of course there's other data that you may want to use in your grading, such as any aerial data or any boundaries. Before we even start grading, we should prepare this data, optimize it as much as possible. So if it's aerial surveys, then we need to find ways to optimize it, because it tends to come in large sized files of very high resolution. And again, that will just slow your work down quite a bit if you try to import that into the software as a background map. Now, afterwards, we have to prepare a concept, or should I say, we have to receive the concept that we need to work with. And this is something that should actually, in many cases, be right here during the brief stage. The reason I have put it here is because, unfortunately, when we're working with people, many times clients don't realize that we actually need that. And so in reality, even though this has to be here, in reality, it is here. And once you talk about the brief and what the client actually requires, and then they need to go and find out that grading criteria and regulations and so on, a concept may have to be prepared because they may not have one, and They may ask you to even prepare it, or they may hire somebody else to prepare it. But in any case, there has to be a concept before we can proceed. And a concept is, in a way, a very simple thing. It doesn't have to at all be anything very fancy. It can even be drawn on a piece of paper. It can be drawn on Google Earth, or it can be very simple, because we're only concerned about two things, and that is the location and the extent of the earthworks that need to be done. And so in the case of dams, for instance, let's say we have a very simple contour map. When we talk about the extent, the location, we just want to know the general location of where that dam is going to be. So maybe it will be here, at this point, and in the landscape. And then we also need to know an extent of at least one of the features of that dam, so that we can deduct all the others from it. And the easiest one to use is just the water outline. So if the client just says, okay, I want a water outline here, they don't have to know the exact size, because that's very difficult to do. And it's actually what grading is about. They can provide you with a simple concept like this and say, okay, I want a water body here. I don't know what size I want it at. I know what volume it needs to be. So maybe they will say, okay, I want this to be 2 megaliters of water volume. And it's now your job to figure out how large this needs to be in order to reach this figure. Because what the client may have provided you right here may actually only be 0.2 megaliters. And there's no way for them to know that until you actually embed it with volumetrics and analyze it in that way. I know I have received in the past many drawings where people have given me, and they have created very elaborate calculations using spreadsheets in order to be able to determine the volume that drawing represents. But when we actually analyze that with grading, even in those circumstances where people have put in a lot of work to be able to deduct the volume of the water body, it's way off from what it is actually when it is analyzed through grading. So it's very difficult to be able to know what a 2D drawing actually represents volumetrically. And this is why I said in the beginning, more than half of the time from all the hundreds of projects we've graded, the concept is way off from what volumetrically from what it actually has to be. And this is why from our experience, between 50 to 70% of all the concepts that we've ever received have failed their objectives, and they had to be they had to be revised. But that was never apparent until we actually graded them and examined them volumetrically. So they may have failed not just because they didn't reach their volumetric objective of, let's say, we want to have 2 megaliters of storage, but there are also other questions that need to be answered. How much is this going to cost to reach? And is this even an efficient structure? And also, an even more difficult thing to predict is not just the volume of the storage, but the volume of, let's say, this embankment that needs to be here. So many people will tend to draw a very small embankment the way they think it's going to look when it's actually built. But when we actually grade it, this may extend way out, depending on the grading criteria. So if this batter is, say, 3:1, then it may extend way out where the client thought it's going to go. And there are implications to that. For instance, if there is something here, like a house, or something else that this embankment is going to impact, then obviously it's not going to work. But there's no way to know that until you actually perform the grading. And so my point with preparing the concept isn't that the client needs to know all of this, but there needs to be a starting point, something that we can begin doing all of this work from. And it's okay if the concept is wrong. It's totally okay. Again, the point of the concept isn't to be right, because, as I said, most likely it's not going to be. It's almost, over 50% certain that it's not going to be correct. But the point of the concept is to be a starting point. That's all it needs to be. And so it's very easy to make a concept that acts just as a starting point, because the goal isn't to spend a lot of time on the concept. You shouldn't do that, because it's pointless. As I said, it will probably not work out. So we just need to do it very quickly. It can be a very basic sketch, just outline where the dam needs to go and just give us a general indication of the water body. And let's use that as a starting point from which we can then see the actual volumetrics, and we can revise from then on. And that will allow us to reach a conclusion, whether that is that the concept just is impossible to work no matter how much we revise it, or we just need to make compromises in order to be able to build anything there. And but before we even get to that stage, after a concept has been prepared, we need to do a preliminary analysis of it. And that just basically means analyzing the catchment and doing a storm analysis. Now, the storm analysis should already be done to a degree during the brief stage. But what we mean by storm analysis at this stage is how the runoff coming from the storm data that we received here is actually related to the catchment. And so if we have a 100-year flood event, how does that event, or how much volume of runoff does that event produce on this catchment onto which the project is based? So if this catchment is 100 hectares of a certain slope and a certain surface cover, how much runoff are we going to get for that catchment? Because we want to know, okay, is it even possible to meet the volumetric demands of this concept? So if the client requires, say, 10 megaliters of storage, is there, in theory, at the very least, is there enough catchment to be able to give us that? If there isn't, there's no point even continuing. There's no point spending any amount of time here doing all of this stuff if the most basic precept is not met. So we just need to do this very quickly, and it doesn't take a lot of time. If you know the storm data, and if you have the survey data, and if you have the location and extent of the dam, then it takes less than 5 minutes to determine, okay, is there even potentially enough catchment to fill this dam? Once you know that, then you can also decide, okay, maybe there isn't enough catchment, and therefore immediately we need to make a revision. We need to move the location, or we need to modify the extent of the dam in order to be able to guarantee or kind of make it work relative to the catchment and the storm data that we have. And if it's not possible, then unfortunately the project has to be scrapped, because if we cannot find the location, or we cannot make a compromise on the extent, or both, in order to make the dam work relative to its catchment and storm context, then there's nothing more that can be done. The project just is not going to work, and there's no point continuing on any further from here. But assuming that everything has worked out and the preliminary analysis suggests that the concept will have enough runoff to meet its volumetric demands, then we can continue. And so it is from this point on that we actually begin our work in Civil 3D in full swing. There is maybe some work that can be done in Civil 3D during the concepting and preliminary analysis stage, but it's not necessary. You can actually do all of this inside of Google Earth, for example. You don't need to use a fancy application like Civil 3D. So from this point on, we're going to now enter in a stage where we are working mostly just in Civil 3D. And it is possible that we may actually have to come back here during the concepting stage if we discover during our volumetric analysis that the concept is just not going to work. It has to be changed, or it's just not going to work at all, and then the project has to be scrapped. But in most cases, it just has to be modified a little, because if you do even a basic concept that is, based on any of the trading that we do in the workplace, most of the time, even if the concept doesn't work straight from the beginning, it just needs to be modified a little bit in order to make it work. And it is very rare that you actually have to scrap an entire project. So as a very first step, then we are going to take the data that we had prepared as well as the concept and import both of those into Civil 3D. And then we can begin working. Once we have imported the survey data, the next step is to create the existing ground surface, or what's called a surface, which is just a triangulated 3D model that is based on the topographic data. And it is that existing ground surface, or what's just called EG for existing ground, that is going to be the foundation of everything else that follows. That is going to be the surface against which we, for example, measure the volume of other elements of the dam, such as the embankment, the spillway, the borrow pit, and so on. It is what will allow us to determine those volumes and, to measure then how much are these elements going to cost, and to get an idea of, do they need to be balanced out? So for instance, does the dam need to be balanced out against the borrow pit? Because it is from the borrow pit that we get the material to build the dam. So if there is not enough material, then we either need to resize the borrow pit, resize the dam, or find another compromise. Maybe we can find material from another place on the site. But in any case, creating the ground surface marks the beginning of actually doing any kind of grading. And so you can see now the grading stage begins. And again, if we watch the video on how to think about grading, you would know that, as I mentioned there, we're going to build things modularly. So we are going to take a dam and break it down to its basic components. So if I go into one of these drawings, let's say this one, because it's more simple, we are going to have several components to a dam. The first one is the embankment. So that will be all of this here. And that will be component, let's say, number 1. Then we are going to have the borrow pit. In this case, the borrow pit actually matches exactly with the water outline. This is not always the case, but in this case it is. So that will be element number 2. And then we are going to have the spillway. And that will be element number 3. And in this case, there aren't any other elements. This is a very simple kind of dam, and it's one of the most basic dams you can do. And so this is actually what our workflow here is based on. It's based on a simple dam. Again, like I mentioned in the beginning, the workflow is going to vary if you have more complex projects that have more than these elements, such as roads and channels and so on. But in most cases, you're probably going to be focusing mostly on very simple kind of dams. And so at the very beginning, we are going to lay out in very simple polylines, just simple lines inside of CAD, the shape of our crest. And of course, that shape is based on the concept. So we could just, in many cases, just take the concept, import it into Civil 3D, and we're ready to go if the concept is actually well defined. But I would say in 99% of the cases, you need to modify the shapes that you receive from the concept because they're going to be very rough. And so we need to lay out our own shapes. And so once we lay out the crest, we can convert that to what is called feature lines, which are special Civil 3D objects that can be embedded with different information such as elevation values as well as grading values. And it is from those feature lines that we can begin to create grading surfaces. So the feature lines in that way are building blocks of surfaces. And this will become important later on when we have to manually, for example, intervene into a grading surface to modify it a bit. Maybe there is some artifacting in it that needs to be refined, or maybe certain parts of it need to be cut out or added. And for all of these things, we are going to use feature lines. And that will become very obvious once we actually start doing the work, which just temporarily brings me to a point, and that is that in this video, I don't expect that you need to learn any of this or memorize it. The points for this video is to serve as a template that you can come back to and reference if you need to kind of remember how we broke this whole pipeline down. Now, once we create the feature lines, we are going to do our very first grading, and that is to grade the crest, fill that in with material, and then we're going to grade the embankment side. So again, what we're going to do is we have established the crest lines. So in this case, that will be the crest, this gray area. And if we look at it from the side, so if we have the existing ground right here, the crest at that point is going to sit above the surface. So we're going to embed that with elevations. Let's say this is at elevation, 100, and down here we have elevation 95. So our crest will be 5 meters above the existing ground from this point, if measured from this point. Obviously, if measured down here, it's going to be higher. And since we're going to, at that point, start grading from that crest, once we converted this to feature lines, what basically we're going to do is grade down from this side and grade down from the other side. And this will give us the side batters. Now, one thing that's going to happen in Civil 3D is that the middle here, where the crest actually is going to be empty. So it's not going to fill, this entire structure is going to be empty. And what we have to do to fill that in is to use a tool called the infill tool. And this is something that you're just going to memorize as you do this over and over again. But it's one of the first mistakes I would say anybody will make, is that they will forget to fill the structure with material, which is going to obviously throw off any volumetric values that derive from it. And so during the course of the program, I will always remind you, we need to now infill something, or infill the crest, or infill another structure, because otherwise it's going to be empty. And so I just wanted to throw that small detail in there. And so once we've graded the embankment, crest, and sides, we can proceed usually to the next step. Now, one small thing I'm going to mention about the embankment, crest, and sides is that we're not just concerned about this side or this side. Remember, this embankment actually has more sides than that. For instance, we have this little side right here. Now, while this may look very insignificant, it is actually a massive influence over the entire dam. And it's not a detail that many people think about or know about. And let me just explain quickly why this is so important. Now, while we're going to look at a valley, let's say we look at this valley right here from this direction, looking up the valley. And what we're probably going to see is, something like this. And as I mentioned, we already laid out the crest. So what we're going to do at the very beginning is just draw a simple line that marks the top of our crest. So let's say this is elevation 100 right here at this point and throughout the entire length of the crest. But if we leave it like that, we make a massive mistake. And that is that we don't include this little side of the embankment right here, the one that goes down from the crest to the bottom of the spillway floor. And so what we have to do is to bring the embankment back a little on one side of the valley, and that will be the side on which the spillway is going to be. So if our water level sits right here, let's say it's 1 meter below the actual crest, then what we need to do is to bring back the embankment. So if I delete this embankment, we need to bring it back so it doesn't actually connect to the existing ground all throughout the same elevation as it does on the other side. One side is going to stay connected, just like we have it here. That's correct. But on the other side, what we have to do is to end the embankment a little bit earlier, and from then we need to grade down to the existing surface, down to the elevation to which the water level meets the existing surface. This point right here is very important, so I'm going to highlight it for a moment. So this point is very important because it's the meeting point of 4 surfaces. One is the water line, then we have the embankment, we have also the existing ground, and finally this is where the spillway is going to go. So we're going to have the spillway floor digging into the side of the existing ground, and from once we lay out the bottom, all we have to do is to grade up to the existing ground. So all of this stuff here is going to be cut out. But again, this point right here is very important because this is where all these surfaces meet together. And this side batter also becomes very important. We need to decide how much that is going to be. We need to have grading criteria for the side batter. Is it going to be 2 to 1? Maybe if it's used for nothing but pedestrian access, we don't need this to be more mild than that. But if vehicles are going to use it, maybe even 4 to 1 may be required, depending on the vehicle. Or if cattle is going to use it, it's also going to vary. But it's an important detail because let's say that we actually had to end it earlier, and maybe we had to end it right here because we need a more mild slope for vehicles. Well, then notice the impact that's going to have on the freeboard that we have between the water level and the embankment. Right here, maybe we have 1 meter, but the more we have this gradation playing out, the less this is going to, the more the freeboard is going to reduce, and therefore the higher the risk that the water can kind of overflow, from over the embankment. And so these are just small details apparently to think about, but in reality they're very important. And I just wanted to point that out. So when we're talking about grading the sides of the embankment, we also include that side. Now, after we've done the embankment, we are going to just repeat this process over and over again for the other elements. So we're going to now lay out the borrow pit. Again, we're just going to lay it out with very simple polylines. And we are going to then convert those polylines to feature lines. And from those feature lines, we're going to grade the borrow pit down to a certain elevation. And before we continue on to grading any other additional surfaces, there is a small intermission right here. And that is balancing out the cut and fill between the borrow pit and the embankment. Again, this is because normally what we want to have is for any material that comes out of the borrow pit, which in this case is this right here. So we want any material that comes from this structure to ideally be able to be used for the embankment to build that. It doesn't always work out, and there's not always necessarily enough good material for building the embankment. That's okay. Your job isn't to make things work. In reality, it's just to analyze a concept and see if that could potentially work. But in any case, this is something that we have to do at this stage. We need to balance out these two as much as possible, because that will dictate if this dam is even going to work. If the volumetric analysis reveals that there's just not enough material to build a dam, then you have to go and talk to the client, and you need to inform them about this so that they can make an informed decision of whether they want to continue the project, and if they do, what compromises are they willing to make. Or if they want to scrap the project, then they just think it's not worth it exploring it anymore. Now, if they do want to continue the project, they may ask you to try different things, to modify the borrow pit in order to get more material. And there really aren't that many things we can do. One is to dig deeper. The other is to make the batter slope steeper so that we can get more material. Or the other is to resize the borrow pit to a larger extent. Or some combination of all of these. And even though we employ maybe all three of those methods, they still may not be enough material. And so at that point, the client may have to think about alternative options, such as getting material from another place on the site. And that is often the case. You may oftentimes have to resort to that. We also may run into another situation where the borrow pit actually provides too much material. And in that case, the client needs to think about what are they going to do with that extra material, because it's going to be expensive potentially to transport it somewhere else, far away from the site. So they need to figure out where they're going to store it and what are they potentially going to use it for. So your job is to inform them about the results that come out from the volumetric analysis at this stage, because it may, again, not be worth continuing the project potentially. That doesn't happen very often, but it does happen, and so the client needs to know about these things. Now, another option could be that just the embankment has to be either reduced or increased in order to either minimize the required material or to utilize material that is otherwise too much. So again, you can see how grading becomes very valuable, because it can save tens of thousands of dollars of work that is otherwise going to be either done for no reason, or it may end up being a disaster. Now, assuming that we have managed to balance out the cut and fill, then we can proceed with the process. If we have not been able to do that, then obviously the project is scrapped. But let's assume that we can proceed. So the next step would be to lay out the water outline. And this may seem very illogical. Why are we laying out the water outline last? Wouldn't that be the first thing we do? It can be the first thing. Oftentimes, that's how you begin. If the entire concept is based just on the water line, then we can lay it out at this stage. But oftentimes, we may also begin from a concept that is based entirely on the crest of the embankment. So the water outline will come somewhere around this stage. And the reason for that is because we need to then start thinking about how much actual volume of water are we able to store in that particular dam. We already balanced out the borrow pit and the embankment, but that doesn't mean that the project is going to work, because maybe we cannot meet the required water volume that the client wanted from all of this. And so once we've balanced out the cut and fill of the borrow pit and embankment, we need to start thinking about this. And so we're going to lay out the water outline if it hasn't been done already. And from there, we're going to create or convert that to feature lines again, just like before. And we're going to convert those feature lines into a surface. And that will allow us to measure how the water surface is related to the surfaces of the embankment and the borrow pit. But before we can do that, we need to merge all of those surfaces. So there comes a stage right here where we are going to, for the first time, to start merging all of the different surfaces that we have in our drawing. And up to this point, we only have 3 surfaces, if we don't count the water surface. So we're going to have the existing ground, we're going to have the embankment, and we're going to have the borrow pit. We're going to merge all of these surfaces together into one single surface, And then we're going to measure the water surface against that surface. Just to illustrate how that works and why we are doing this, now let me draw from the side. Let's have a cross section. So let's say that by this stage, what we have is the existing ground. We also have, let's say, the embankment. We have graded that. And we have the borrow pit. Let's say we have graded that something like this. I mean, in reality, it should be balanced out with the embankment. So let's say we have something like this. Now, the reason why we have to merge all of these before we can measure the actual water volume is because the way Civil 3D works. Let's say that our water level is sitting right here. And if we try to measure the water level right now, before actually merging all of these surfaces, what's going to happen is it's only going to measure it against the existing ground. Because the way Civil 3D works is it projects kind of volume down from this water line and fills that area until it hits a given surface that we have specified. In this case, we have specified, let's say, the existing ground surface. So that is what it's going to measure against. And you can see, obviously, that excludes a lot of information, such as this entire empty space here, that where we had the borrow pit. It also excludes the fact that the embankment is in the way. So there is a certain volume here that it should not be included in the calculations, because that's where the embankment is standing in the way. And so to be able to make Civil 3D actually measure against all of these other surfaces, we need to first merge them together. So what's going to happen is we're going to have a brand new surface, which is going to have the existing ground, the borrow pit, and the embankment all together in one surface. Something like that. And so now when we take our water level and we project volume from it, it's going to measure against all of these surfaces. It's going to factor in the fact that there's the embankment in the way and that we have also, the borrow pit dug out there. And so all of this is going to be factored in the volumetrics. And so this is why it is at this stage that we merge all of those surfaces together. And then you can see we can compare the merged surfaces against the water volume surface. And we're going to be able to get out volumetric results from this. And then we can come to our client and we can say this is how much water volume you're going to get from this dam. So it is at this stage that we can get these results. Then we go to our client and we tell them that, and if they are not happy, then we need to do a major revision. And that is, we need to begin from here, back at top of this part of the pipeline. We need to recreate potentially the embankment or the borrow pit, or both of them, because just changing one of them may not be enough to get the extra volume that the client wants. Or maybe there is too much volume and we are now passing the threshold of the regulatory criteria, which allow us to only have within a certain amount of volume before we hit a certain regulatory threshold. And that may be very expensive. It may require engineering oversight, which many people want to avoid, again, because it's expensive, and so on. So there are many factors at play here, but the point is that we need to make modifications. We need to make revision of the borrow pit and the embankment. And then this whole process repeats again. We still, again, reach the point where we merge the surfaces together, which in Civil 3D is very easy because Civil 3D will remember that you have merged those surfaces in the past and will simply update them with the new ones. So that's nice, and you don't have to necessarily do that again. And then we get the new results of the revisions that we made. Again, we come back and tell the client. If they're not happy, we again repeat this process over and over again until we reach a scenario in which we have arrived at the volumetrics of the storage that the client wants. if it's even possible. And if it's not possible, then we have two options. One is to revise the whole concept and start from here again. And the other option is, if that is not something they want to do, then the project just doesn't work out and it has to be scrapped. Now, assuming that everything worked out and we've done any revisions necessary and we have arrived at a water volume that the client is happy with, we can proceed to the final stages of a basic dam. Again, there may be more stages if the dam is more complex, so we may have to tie it in with roads, or we may have to tie it in with channels, or we may have to tie it in with other dams that are part of that landscape. But this is a very basic dam that we're talking about now, a very isolated kind of system, just one that is standalone. So the final stage of that will be to lay out the spillway. And again, just like before, we're going to use simple polylines. We're going to lay out the spillway shape. We're going to convert that to feature lines, and we're going to grade from those feature lines the spillway surface. Once we have done all of that, we can merge all of the grading surfaces we have. So that includes the ones we previously merged with the spillway as well. And from there, we can also derive volumetrics for each of those surfaces separately, as well as for them together. And we can then reach the export stage, which is this final stage right here. So all of this stuff. We have an export surface data stage. So it is at this point where we can start exporting all of our drawings or all of our surfaces from the drawing to different file formats. So for instance, we can export them to, let's say, XML if they need to be plugged into auto steering machinery for automated grading, or we can export them to a shapefile or to KMZ or whatever else is required. It can also be a DEM and so on. So there are many files we can export them to. For us, it is very important to be able to export at the very least to shapefile and KMZ, because these are very popular formats. Especially KMZ is very convenient for clients. Ideally, we would want to export all of our surfaces to KMZ so a client can preview, and we can kind of spend some time to embellish that KMZ file so that it will contain all of the volumetric information for each of those surfaces, as well as for the entire dam system as a whole, so that when the client opens that KMZ file, it very conveniently shows everything there for them. They don't have to have any special software to be able to preview that. We can also attach to that KMZ file any drafted sheets that we have made during the drafting stage, and this is a module all on its own in this program because it's a rather big thing. So I separated that in its own module. So if you're interested in drafting, you can check that out. This is basically where we prepare construction sheets or just sheets for presentation. But again, the drafting is actually a byproduct of all of this stuff that we did before that point. And we can also prepare spreadsheets from the surface and volumetric analysis that we have done for the dam, and we can export those out, as well as we can also prepare maps of the surfaces that we've created. So if we want to have slope maps or flow maps or aspect maps or visibility maps, we can prepare those from the surfaces that we have created. So we can give the client more information about how this new structure is going to stand in the landscape and interact with that landscape. And again, so finally we can send all of this data to the client or a contractor for actually implementing this structure. And this is the entire pipeline. And again, this is for a very basic dam like this one. It doesn't have any channels or special structures in the embankment or the borrow pit. It doesn't have any beaches or roads or stuff like that. It's just a very simple basic farm dam, and it's probably the bread and butter of all the work that you're going to do in grading. So this is what this pipeline is based on. I hope that this pipeline has given you kind of overview of the water storage grading process. Again, many of these things are going to make sense during the course of the program, I hope. And if not, then we can always talk about it, and I can provide more support, more videos and information. But I hope this video serves as a reference that you can come back to and always find your way if you ever get confused of where we are actually in the process. And this entire document is also available to you. It's in the description of this video. So thank you for watching. Thanks for sticking through. I hope this has made sense. I know grading in a way is not complicated once you get it, but just getting to a point where you connect all the dots can be a little bit confusing. So I hope this has helped in orienting you. Thank you for watching, and we're going to continue in the next video with another pipeline.